Okay, everybody. So if you start today by taking a quick look at this sheet from 2 days ago, where you calculated different values for the characteristics of a falling object, this sheet gives us a clue as to what today's work is about. So let's take a quick look at this. I've got the numbers worked out and I posted this. So if you had worked the sheet out correctly, you're going to know right away that you did it correct when you get to the end of it. The first column, you're calculating how fast the object gets as it falls. So you're going to get values that get bigger, 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 bigger all the way down. And none of those numbers really look like they mean anything in this situation. Next, you're going to calculate the distance that the object fell in the amount of time. And of course, if you do it right, at the very bottom, you're going to get 78.4. I see I made a typing error there when I put that in. That's supposed to be a 4. I'll have to correct that before I post it for you guys. But obviously, it's going to fall 78.4 meters at the end of the time because that's the original height of the cliff. So that's a number that you're expecting to see. Now, this is distance fallen, whereas the third column is the height. In other words, kind of the opposite. How high is the object? So when it gets to the very bottom, it's obviously at a height of 0. And the formula works out that way. And during the fall, you've got these various heights that get smaller and smaller and smaller as it goes down. But none of those heights really match up with any of the other numbers on here and don't seem to mean anything else. It's not until you calculate the energies that you start to see what's going on here. When you do kinetic energy, 1/2 mv squared, you will get a successively larger amounts of energy, and they end at this very specific number here, 30,732.8 joules. Again, that doesn't look like it matches anything on the page. However, when you calculate the gravitational energy in the beginning before it starts to move, it has that same 30,732.8 joules. And as the object falls and goes to a lower and a lower height, the gravitational energy drops. And as that gravitational energy falls, the kinetic energy gets bigger as it goes down. And when you add the two energies together in the end, this is the important part of this entire sheet. You get the exact same amount of energy all the way down, no matter what position you look at. So this right here is, in a nutshell, that's what conservation of energy is. Conservation of energy means that in a situation where energy changes from one form to another, you don't lose a single joule of energy. All it does is it transfers from one form to another. But if you could collect together all the different forms of energy and put them back together again into one, you find that energy is a constant in a situation. It's finite. It conserves. And so even though the gravitational energy gets smaller as it goes down, the kinetic energy gets larger as it goes down, and it's not an even transfer, as you can see. But when you add those two energies together, you discover that it's the same amount of energy no matter what position you want to look at. And that's the important part for today. So I posted these sheets. We're going to do 2 quick examples. And today's work, actually, I changed the heading at the top of this page and made it grade 11 university physics. This sheet is actually a grade 12 college sheet. So today we're going to start off with some easier work that has to do with this that the college students do. And then on Monday, we'll get into a little bit more of a difficult mathematical analysis, and that's when we'll match up with that example that you were looking at in the book yesterday. So today, don't worry about what you read yesterday. We'll kind of save that for Monday. And let's go through 2 very easy examples. And remember, if you were in the college class, the grade 12 college class, there are students in that class that didn't take any math since grade 10, and they're in the college physics class. So that should give you a hint of how easy this is going to be. It's going to be very easy math that you've already sort of done, but let's see how this works out. First of all, the law of conservation of energy. You want to write that down right out of the textbook. And I'm not exactly sure what the textbook said. I didn't review it, but the important points for law of conservation of energy is energy can't be created or destroyed. Energy cannot be created or destroyed it can only transfer from one form to another. I should have had this written out beforehand, sorry. It can only transfer from one form to another. From one form to another. So that statement right there will allow us to do some calculations using energy that you won't realize you can do until you try them. For example, you throw a ball up into the air at 50 meters a second. How high will it go? That should sound familiar. That should sound like a question that we already did earlier in the course, and indeed we did, so I put 2 headings here. I do want to remind you that you can solve this with kinematics, because we did this before. Let's start there, actually, just to show you. If you throw a ball up in the air, that's the initial speed. So the initial speed leaving the ground is 50 meters a second. And if you throw it up and it goes up to its maximum height, because that's what this question asks, how high will it go? The V2 will be 0 when it gets to its maximum height. And because it's a free fall situation and it has to do with gravitation slowing it down, we know that the acceleration is 9.8 meters per second squared. And this isn't a G value in the formula that we're going to use. It's an A value. It's an acceleration. So we'd have to put a negative here for slowing down at 9.8 meters per second squared. And if we were calculating how high it travels, that's the distance up in the air. So we did this. You would search your 5 acceleration formulas and look for the one that doesn't have time in it, because there's no t mentioned in this givens list and it's not the requirement to solve. And you would look up the formula and rearrange it. So I'm going to skip a step here and go straight to the rearrangement of the formula. V2 squared minus V1 squared divided by 2A. And just do your substitutions. There's no unit conversions to make here at all. On the top, make sure you don't mix up the order of the V's. V2 is 0 meters per second squared. There's a minus in the formula that doesn't go away when you square the next value of 50 meters a second. And that's why you have to remember that acceleration is slowing down with a negative, because you're going to need that negative on the bottom to cancel the negative that results on top after you square that 50. So work that out on a calculator. And this is pretty funny, but my son stole my calculator off my desk, so I've actually got to get one. I'll tell you what, you guys work that out for a second. I'm going to get a calculator. I was lucky. There was one in the drawer beside me. I didn't have to run upstairs. I feel so silly. Okay, 50 squared divided by 2 and divided by 9.8. The signs work themselves out. We're going to get 127.55 meters up into the air. And if this was the first month of the class, that would be it. You would do the calculation and be done, and we did this before. But now let's use energy analysis. Knowing that that's the answer that we would have got in the first couple of weeks in February, let's look at how the work that we did just this last week could be used to solve this. Okay, so you throw the ball up at 50 meters a second. So it's leaving the ground with no height whatsoever. It's at 0 meters high, but it's leaving the ground at 50 meters a second. The entire energy at the ground is kinetic energy because it's moving 50 meters a second. When it gets up to its highest point, it won't have any kinetic energy anymore. The energy will entirely become gravitational energy. It'll slowly change all the way up, but when it gets to its maximum height, all of the kinetic energy that it had at the ground will be transferred into gravitational energy. Actually, they tell you to start with a line that looks like this. The total energy in the beginning, and I'm just going to shorten that, total energy in the beginning has to equal the total energy at the end. That's the law of conservation of energy. You're not going to lose a single joule of energy. So if you can calculate the energy in the beginning, it must equal the energy in the end. Even though the form of energy is going to change, just like on this sheet. where the energy continuously changed all the way down, but it was always the same amount of energy. So same thing here. We don't need to calculate what the energy is. We just need to understand that this is true. The total energy in the beginning has to equal the total energy in the end. And if that's true, just make your substitutions for what kind of energy you have. So in the beginning, if it's being thrown up into the air at 50 meters a second and it hasn't even left the ground yet, all of the energy in the beginning is kinetic. At the end of the question, when it reaches the highest point, and it gets slower and slower and slower as it goes up, when it reaches its absolute highest point, it will have no more speed, and all of the energy at that point will be gravitational potential energy. Now, if you understand this right here, that's the whole thing. That's the main gist of this entire work. And that's not a formula you'll find on your formula sheet, because it isn't a formula. It's equating two variables that you already know the formulas for. So this expression means that the kinetic energy that it has being thrown up into the air at 50 meters a second, if you worked that value out, it would equal the exact same numerical value as the gravitational energy at the very top. But we're not going to work this out. We're just going to sub in our formulas. Now you flip to your formula sheet. Kinetic energy is 1/2 mv squared. And on the other side of this formula, gravitational energy is mgh. There's only going to be one unknown in this expression. We're solving for this. We're solving for how high up into the air is this object going to go. So when you write an energy conservation formula and you sub in your sub formulas off your formula sheet, you'll have an expression on the page where there's only one thing that you need to solve for. And all the rules that you've learned in math from grade 9 and 10 apply. Like, for example, in this case, there's an m on either side of the equation. So it doesn't even matter what the mass of this ball is, because m will cancel out, left side, right side. So we're solving for h. That means that the g here didn't cancel out. It looks like I canceled it, but I put a circle around the h. In order to solve for h, we have to isolate for h. And that means moving g to the other side, and it's in the numerator on this side. When you move it over, it will be in the denominator. So technically, that formula right there, with substitutions, should give you exactly the same answer. It has to. I mean, that's physics. If it's 127.55 meters high, losing all of its speed, we have to get the same answer here. And you will, of course, when you sub in the speed in the beginning was 50 meters per second squared, and gravitational acceleration is 9.8 meters per second squared. And you never make gravitational acceleration negative, because you don't have to consider whether it speeds up or slows down. That's just the gravitational acceleration on Earth. And when you work this out, right down to the decimal place, you're going to get exactly the same value. I'm subbing it into a calculator. I don't know why. I know it's going to work out. 127.55 meters. You get exactly the same answer. Now, I'm not saying that the old way is easier or this energy way is easier. It's just two different ways to get answers to the same question. And as you move on in future physics years, grade 12 and on, you'll find that you can start using whatever strategy you wish. Things get very open-ended, and it stops being these exact little questions where you have to do exactly what an example in the textbook says. So you'll find that sometimes you'll use kinematics, and sometimes you'll prefer to use energy. Right now, though, you have to learn how to do the energy method just to show that you can do it. Let's try another example. Let's just go the opposite way. We'll start up at the top. What if you drop a 40-gram object from a height of 60 centimeters? What will be the speed of the object when it arrives at the ground? Well, you could do this in the first couple weeks of this course. And you did do this. I could have asked you this question before and just deleted the 40 grams because that wouldn't have been important. You would have done it with kinematics in the past. Your V1 would have been 0 because you're dropping the object. The distance that it falls would be 60 centimeters. and you would convert that, divide by 100, 0.6 meters, and you're looking for final speed, so V2 equals what? Question mark. And there's no time given. The unknown variable would be acceleration. It's gravitation. It accelerates 9.8 meters per second squared on its way down. So, one more time, we're using the same formula as the last example. Solving for V2, you would have done this earlier in the course. You would have looked at your formula sheet and said V2 squared equals V1 squared plus 2AD. And make your substitutions. I'm going to write it like this. I always prefer to, even though the formula sheet shows it like that, I prefer to write it like this so that I don't forget to square root it when I get to the end of the question. And just make the substitutions here. V1 is 0, so I'm not even going to show the substitution for that, even though you should. 2AD, so 2 multiplied by A, which is 9.8 meters per second squared, multiplied by distance, 0.6 meters. And root the entire answer. So, work from the very first couple of weeks of the course tells us that in the end you have to get an answer of 34.29 meters per second. So now the question is, can you successfully use energy conservation strategies to get that answer, knowing that this must be the answer from earlier in the course? So let's do it the energy method. And again, the suggestion when you're using conservation of energy is always to write this very first line. You don't need this line. Total energy in the beginning equals total energy in the end. But if you write this, it kind of reminds you when you look back at your work what exactly you were doing. So, total energy in the beginning. If you start off with a 40-gram object and it's not moving, you're just holding on to it 60 centimeters above the ground, all of the energy in the beginning is going to be gravitational. You have it lifted up to a height of 60 centimeters and it's not moving yet. You're about to let it go. When it gets to the end of this question, it will have fallen all the way down to the ground. And just before it hits the ground, of course, you got to think that way in physics all the time. Just before it hits the ground, it will be traveling at a very fast speed, or its fastest speed, and it will be traveling at its fastest speed, and it will have no height whatsoever. So the total energy in the end is going to be all kinetic energy. Sorry, I'm pausing because I'm realizing, nothing's wrong here, by the way, I'm realizing as I'm thinking about this question that this is a very, very fast speed for 60 centimeters of drop. I think there's a mistake here. Well, let's look for that later. Let's finish this question and see if the answer matches up. It doesn't feel right. And I would stop the video and just re-record this entire video. But no, I want you to think like this all the time. If an answer maybe doesn't feel right, you always got to check it. And normally I would go through this calculation again, but I am going through this calculation again, doing it the energy method. So let's see what happens, and then we'll find the mistake in the end if there is one over here. Okay, so this idea holds. This is not the same formula as the previous example. It looks the same, but flip the page back and you'll see. So you never memorize this. You just have to think. Total energy in the beginning equals total energy in the end. You're holding on to it in the beginning. It's got gravitational energy. In the end, it drops all the way down to the ground. And just before it hits the ground, it's got kinetic energy only. It has no height when it reaches the ground. So now you flip to your formula sheet if you need to, and you put in the formulas. Gravitational energy is mgh, and kinetic energy is 1/2 mv squared. Identify what the unknown is. What will be the speed of the object when it arrives at the ground? That's this here, v. And all you have to do is rearrange and solve for that speed. There's a mass on either side of the equation, so that cancels out. So even though 40 grams was given as a mass in this question, it's not even going to matter in the calculation. Okay, isolate for v. So there's a 1/2 here on the right Then I'm going to move to the left. And again, there are different ways to rearrange when you have fractions. I prefer to just move the entire fraction and not even think about flipping it over and putting it on top. It's a numerator here. I'm going to move it to this side and make it a denominator. That's going to isolate for v squared. And let's, instead of writing v squared, I'm just going to do this. Root the entire left-hand side of the formula. And then it's just set and ready to go. So let's make the substitutions here. G is 9.8 meters per second squared. The height in this question, it's dropping from 0.6 meters. You divide by 1/2, which you can write as 0.5 if you like, if that makes it easier to calculate. And you have to take the root of that entire equation. So I'm doing this off to the side. And we get a final answer of V equals 3.429 meters per second. Now that sounds more realistic. So what's the problem here? I can see that like these have to be the same answer. They're not. And I can see they're off by a factor of 10. So I either misread my calculator, which is totally possible, or I punched in one of these numbers wrong. So let's try it one more time because they have to be the same. So 2 multiplied by 9.8 multiplied by 0.6. Maybe I punched in 60 before. And take the square root of that answer. Does give you the same thing. So I don't know what I did. I either misread the calculator or maybe I didn't punch in 0.6. Maybe I put in 60 by accident. But this answer is 3.429. They equal. So again, two different ways to get the exact same answer. You can use the old method or the new energy calculation method when you're faced with a choice. But because we're in grade 11 physics and you have to learn the curriculum as it's set, you have to understand how to do the energy method right now. And then you can open it up and use whatever method you want in the future. So today there are only 3 questions. The first 2 questions are very much like these 2 examples. There's just some minor things different, like for example, unit conversions are slightly different. And question 3 is a little bit different than these 2 examples, but I wrote a hint right in the question to tell you how to do it, and you just have to work your way through it. So sorry, this is a little bit longer of a video than usual, but it's more instructional. And then the practice questions, these practice questions should literally take you 15 minutes at the most. So please don't not do them if you feel like you've already invested enough time on the video. It's very quick practice, and even question 3, which is a little bit longer, is altogether, they're only going to take you 15 minutes. And that'll be it for the weekend. So have a good weekend. And on Monday, we're going to go back to this work. We'll take up these questions. We'll go back to this work, and it's going to get slightly more mathematically advanced, but the idea is going to be the same.